Basically, we're going to talk about positioning, distance measurement, and also other measurement solutions. This one's going to be a little bit different, I think. I hope. So I hope you get something out of it. If you have any questions, feel free to ask, and I will try to answer them. If not, I know some guys in tech support that can answer these questions really well. So, anywho, also some of this stuff in this presentation actually came from Scott Rosenberger. So I know Scott's on vacation today, but a big thank you to him for giving me some of this information. So as soon as I figure out how to do this, we will move along. So by the end of this, we're going to, by the end of this presentation, we're going to discuss some measurement definitions, some terminology that might come in handy for you, some application type things you need to consider. And we're going to discuss distance sensor solutions and positioning sensor solutions, along with other measurement solutions, and then also a review of level detection. So again, hopefully this will help you out. So how does Balluff define measurement? So first thing is positioning. So we're using a sensor to provide feedback. Typically with positioning, the sensor is actually part of the movement. So it's the sensor is actually going to be, or some component of the sensor is actually going to be on a moving item. So that's positioning. The next one is motion. So we're using a sensor to provide updates to some sort of controller to indicate position, speed, or direction. And then the next one is measuring. So we're using a sensor to accurately determine displacement or length of an object. So for instance, if you have a cutoff machine where you're cutting tubing to a certain length and you want to know what, you have to measure that length and put it into a controller, we use that. And then the other one of key importance is distance sensing. So with distance sensing, we're using what we call a standoff sensor technology, if you will. So basically, this is going to be something like a photoelectric. Okay, the sensor is mounted off the moving device, and we're shooting a light beam at that target to determine what that distance is. So we're not positioning anything, but we're looking at that distance. So again, you're going to run into products like photoelectrics, inductives, capacitive, ultrasonic to determine that distance. And then the last one is rotary position. With that, you're going to use some sort of an encoder. Could be an optical encoder, could be one of our BML type encoders, but we're going to use that to determine rotational angle or speed, or actually even could be a distance as well. So a lot of different ways to define this stuff. So positioning versus distance. So with positioning, the actual position of the target, or in this case, could be the position of the machinery, could be a target, it could be a scale reader, it could be a digital display. So basically, you want to know where it is right now, and then if it moves, where is it then? Where is it now? Once it's moved, and then if it's moved a third time, where is it? So this is going to be stuff like BTLs and BMLs, devices that are actually mounted on the moving piece of equipment. The next one is distance measurement. So with that one, we're reporting the distance to the object. Again, this is the prime example is a photoelectric. So we got a sensor. We're going to shoot a beam of light out at the target. We're going to measure what that distance is. And we're going to report that back to a device. Typically with all of these, it's going to be some sort of an analog signal or through IO link, but it's going to be some sort of a dynamic or continuous value that we're reporting back to the controller. Could be a PLC, could be whatever. Some measurement terminology basics. So we're going to run through some of these formulas just to, just give you a flashback to school. Actually, I'm kidding. We're not going to. So the first one is resolution. So resolution is the smallest increment uh, of change that can be detected and indicated by the output of the sensor. Okay, so this could be done and depending upon the device, it could be in the microns or it could be in the millimeters or worse. So this is the smallest increment that can be moved, that an object can move, and us still be able to detect it. The next thing that comes into this is repeatability. So repeatability is if we move an object to a certain point many times under the same conditions and we get the same or very close value, that's repeatability. If the value is jumping all over the place, that's not repeatable. Sometimes this is called repeat accuracy, but it has to get to the same position under identical conditions. Then we get into accuracy, and this is what a lot of folks refer to. Uh, some customers will say, hey, I need the accuracy of 1 micron. Well, basically, that's resolution. So accuracy sometimes can be referred, some customers might refer to accuracy as resolution or nonlinearity. Could be any or all of those. For our purposes, we look at the precision. Okay, so what is the actual position that you're seeing? So another way to look at this is if you like to shoot weapons, for instance, we have a target, so we're going to shoot at this target, and as you see, our shots are in the upper right-hand corner there. They're kind of all over the place. So is it accurate? No. Is it repeatable? Not by a long shot, so to speak. Sorry, the pun. The next type of target is we've basically moved that pattern down to the lower left. So is it accurate? Still not accurate. It's still not repeatable, and it's still not precise. Once we start getting our pattern more tight, it's still not accurate because we're shooting for the bullseye, right? But it is repeatable. At least that pattern's pretty tight. And then what we're actually striving for is this: is it accurate? Yes. Is it repeatable? Very much so. And it is precise. So this is the things we have to look at. And again, a lot of customers get the accuracy and resolution and sometimes repeatability all mixed up. So you really need to dive into that with them to find out what they're really looking for. As I mentioned earlier, typically with these devices, you're going to have an analog output or again, IO link, in which case some of this doesn't, is not affected by, or IO link's not affected by these. But typically with analog outputs on our devices can be 0 to 10 volts or it could be 1 to 10 volts. The advantages of an analog output that's voltage is it's easier. Basically, you take your wires, hook them up to your input device. Could be an analog input card. It could be a controller of some sort, but it's relatively easy. And there's just a lot more interface devices out there for voltage type outputs. The big disadvantage to voltage is cable length. Typically, if you're doing a voltage output, your cable length should be 50 feet or less. Also, it should be a shielded cable. And this is one thing you really have to watch out for with some of our photoelectric sensors, our BOD sensors and so forth. Is a lot of times we say, here's the cable you use, and sometimes it's an unshielded cable. So you really need to watch out for that. You need to find out how they're going to route cables. Hopefully they've taken care of that. Years ago, I used to call them paper mills and steel mills a lot, and it was amazing to me how many times I go into like a paper mill, for instance, and they would run a voltage cable, 100, 150 feet and say, hey, we're having problems. We're supposed to get 0 to 10 volts, and we're not because of voltage drop. We're getting, maybe 0 to 8 volts as opposed to 10 volts. So the cable length can be a real big problem. And again, sometimes you do have that voltage drop. The other one is a 4 to 20 milliamp output or milliamp output. The advantage to that is you have great noise immunity, whereas with voltage, noise can be a big problem. There's no voltage drop with the analog output. I mean, with the current output, and you don't lose any signals or that much signal loss. The disadvantage is these are typically a little bit more difficult to work with. You know, if you're hooking meters up to them, you have to hook up your meters a certain way. So sometimes these can be a little bit more difficult, and sometimes temperature can affect the current a little bit. Some other considerations or things that you need to talk to customers about is environmental conditions. This is big in some cases. I'm working on some projects right now on BTLs where BTLs are being used in some very high shock, high vibration applications, and components are breaking and so forth. So you need to find out what the environmental condition is like. What's the temperatures range going to be with those? If there is the shock and vibration, what's the magnitude or how often is that going to happen? And also what kind of liquids or corrosive material might be around that particular device. The other thing that you need to talk about is the electrical. What kind of interface do they want? Do they want to go IO-Link? Do they want to eliminate the analog cards and that stuff that they're dealing with and go with IO-Link, or do they want to keep with an analog type signal? Their power supply. Do they also want some digital outputs? Again, with our BODs, we can also get an analog output. And we can also get a digital output. So you can actually use that digital output to set an alarm that you're getting too close, or you're getting ready to have some sort of over travel. And then also EMC or noise that might be around that device. Mechanically, how are they going to measure it? Physical size, the machine precision, the tolerances that the customer is looking for, and then the overall length, because the overall length is obviously going to drive what technology we go after. To me, technology drives the application drives the technology. So once we find out all this kind of stuff, then we can find out what kind of technology. So the last thing that I think should always be addressed, kind of, sort of, is the commercial aspect. Obviously, you want to know what the budget is going in up front, but until we know exactly what technology we're going to use, we really can't throw prices out there that much. Obviously, a customer is going to tell us what kind of range he wants to be in, but it's kind of the last thing. Let's get it to work first, and then figure out the pricing later. And then also the technical skill level. Do they have the guys on hand that can support this, or are they going to need some training from us and so forth? So there's a lot of things to consider once you're starting to do this distance and positioning measurement. So let's talk some distance sensors. So basically, what we have here, these are what I consider the distance sensors, the devices that are not going to be mounted on a moving piece of equipment that much. So first off, we have inductive, the BAW sensors. Typically, these are going to get about a max range of 60 millimeters. This one, I would expect a couple of comments about, are you serious? Yes. We can do distance measurement with capacitive sensors. If you're doing it with a BAW, it's going to be a metal object. If you're doing it with a capacitive, it can be anything. I do know that we've used some capacitive sensors to do loop control on some pieces of equipment. It's a tough application, but it can be done. You'll notice here that I'm saying that we can detect distances up to 850 millimeters. This is basically the strip sensor, and you'll notice that I have a tank drawing out here. So the sensors where you see this, or sensor families where you see this tank, that indicates that we can use it in level applications. So capacitive, that's where I'm getting this 850. Typically, if you're using one of these devices, it's going to be in the 50 millimeter range. The other one, ultrasonics, can be up to several meters. In this case, up to about 8 meters. And then we can also do BODs that we can get up to 20 meters. So these are the different products for distance measurement. Once you start dealing with photoelectrics, there's a couple things you have to address with this or keep in your mind. Is the difference between triangulation and time of flight. So triangulation, basically what happens is the sensor emits a light. The light hits the target, bounces back. It hits the photo sensing device, and then what we do is we actually measure the angle for, where the light reflects back onto the sensing device. So the greater the angle, the closer to the device, the farther the angle, or farther the device, the smaller the angle. Some advantages to triangulation is the fact that you get better resolution. Typically, the small light diameter, typically all of these are going to be with laser. In fact, all of our distance sensors are laser. We don't have any that use infrared. We do have one that uses a red light. So typically, triangulation is going to give you a lot better resolution. The limitation is short to mid-range. So typically, once you get above maybe 2 meters, you're back into time of flight. So these are going to be short. They are also susceptible to your target characteristics. So whether or not you have contours, your light might bounce around the wrong direction. And typically, you want a clean environment with these guys. The other one is time of flight. So it works basically the same way. The sensor emits a light, hits the target, bounces back into the sensor, and in this case, we measure the time that the light went out. Light has a constant speed, so we just measure that time, and that determines what the distance is. These are more immune to target characteristics. They still can affect it. If you have dark objects like tires, for instance, sometimes you might not get the distance that you want out of them. And it has longer range. So our 20-meter version is going to be the longer range. It's going to use time of flight. Typically, they're a little bit slower on the measurement rate, and also they have lower resolution than what the triangulations have. So let's look at the photoelectrics. Here's the only one that's a red light. So the BOD 6K only has a range of up to about 200 millimeters. The resolution on it varies depending upon which one you use. So as low as 120 microns up to 680. There's 5 different versions. They have different style connectors. They're all voltage. None of them are current. They all have a discrete output, again, so you can set it up so that, give me a warning when I'm getting too far away or too close. These are also Ecolab. So for your PFB folks, you got IP67 and IP69K ratings. The other one is the BOD 26K. There's 10 different versions here. In this case, we got voltage, we got current. We also have an RS485, which I do not see used very often. Still have discrete output. The 21M, these are going through some engineering changes or some redesigns. So with the 21M, there's 7 versions. The latest version is primarily IO link. You can do a lot of things with this one. You can do some statistics. You can look at curves and so forth with it. So the 21Ms are becoming again, being redesigned. As they're redesigned, they're going away from the silver housing to the black housing. You can get ranges up to about 500 millimeters, resolutions anywhere from 30 microns up to 500 microns. 24K, this one's got the digital display on it. So there's only 2 versions. Again, it's voltage or current or IO link. You get ranges up to about 650 millimeters. The 66M is a triangulation sensor. This one is one that goes up to 200 millimeters, 2,000 millimeters. So resolutions can be as low is 100 microns up to 1 millimeter, depends upon the version, either voltage or current. That's your only choice there. And then the other one is the 23K. So the 23K is another one that can be used in PFB applications. There is an IO Link version. The resolution on these is not that good. It's 5 millimeters, which in some applications will be sufficient, but it's not as good as the triangulation, obviously, because this one is a time of flight. And then last but not least is a 37M. This one's got a digital display on it on the 20-meter versions. There's a 10-meter version that does not have a display. Same thing here. You can get voltage, current, or RS-485 output. You'll notice that I put the tank over here, so we could use these guys for level applications. Could be if you're detecting levels of solids or levels of liquids. There are ways to do that. If you're going to do liquids, typically you want to put a floater or something in there, capture that float, and then read your levels that way. Other distance sensors, again, are the BAWs. There's basically 57 different versions of the tubular style, 10 versions of the block styles that you see over here on the right-hand side. Up to 50 millimeters is about the max range you're going to get out of here. Again, you got the same thing, voltage, current, or IO Link. And here's the capacitive. So if you want to do distance measuring with the capacitive, you got to use the remote amplifier. I just lied to you. Anyway, you got to use the remote amplifier for these versions down here. Or there is one tubular style. It's an 18 millimeter that provides a 0 to 10 volt signal out. This is the one that we've used on loop control. But you also have a very short range, typically about up to 15 millimeters. And then you've also got the ability to do distance measurement for continuous measurement for tank levels using the strip sensor. This one sets us apart from the competition. Nobody can do the strip sensor, and also nobody competition-wise can do analog with a capacitive sensor. Sets us apart by a long shot. Ultrasonics, there's tubular styles. There's about 48 different styles. There's 8 different block styles. These are absolute. It's one of the things I didn't talk about. So you also have incremental and absolute. Incremental means if you lose power, it doesn't know where it is. And you also typically have to home the device. Absolute, if you lose power and power is restored, you know where the device is. So ranges here can go up to 8 meters with the ultrasonics. More information on the ultrasonics at a future date. Positioning sensors, no questions so far. So positioning sensors. The first one is the BIP. You'll notice I did not put the BIL on here, but the BIP is on here. So with these guys, you can get up to about 133 millimeter range. The BMP, you can get up to 256 millimeters. I'm actually running into a couple applications where we're actually modifying this BMP for certain customers, changing some firmware and so forth. So BMP seems to be a very interesting product, a lot of interest in it. Hopefully we can still continue to get them. Magnetostrictive transducers, the BTLs. I will admit I do not know that much about BTL, so if you have any questions on these, please feel free to reach out to Mike Belts or Scott Rosenberger. They would be happy to help you with any questions. But anyway, with these guys, we can get up to about 7.6 meters. And then last but not least are the BMLs, 48 meters with these guys. So with the BIP, we have 32 different versions. This is absolute. We can get, like I said, We can get analog, we can get also IO link. Typically, these are going to be used in gripper jaws and so forth to know what the position of the gripper is in this case. Or you could use this for force. So let's say a gripper is picking up an aluminum can and you know that there's a certain force or a certain position on that gripper, you're going to start smashing the can. So you could use these devices to eliminate damaging product. Mobility, packaging, a lot of applications for these, especially in the gripper format. Magnetic positioning with the BMP. So there's 27 different versions, basically 8 lengths, so you can get voltage, current, or IO link. Seen these being used a lot in valve positions. So basically, these are going to be used on any type of cylinder. Seen some customers actually using external magnets with these guys. So again, you're going to use these for positioning or any type of linear motion. And then BTL, as you're all aware, we have a whole host of BTL versions and solutions out there. These can be used in level applications, typically with a float. But again, if you have any questions on these guys, feel free to reach out to tech support folks. And then the magnetic, or the BMLs. So the BMLs, one of the things I want to tell you before I forget, they're actually coming out with some new standard disc for these guys for positioning and so forth. So look for that. It should be coming pretty soon. Also, Chris Everline just put a message up there that there is a new basic BTL style coming. It should be out December of this year, because Chris put down 2021, so we're going to hold him to it. Anyway, with the BMLs, so we can do linear and rotary applications. You can get them as incremental or absolute, or there's different hybrid interfaces for these guys. Again, we've got a lot of products there for positioning.
Jack?
So, yes.
Tim had a question here. How stable is the measurement value using a capacitive sensor given that environmental conditions, i.e. temperatures, can have a major impact on capacitive sensors?
This is true. Temperatures can affect capacitive sensors. So that's one thing that falls in those application questions, is find out what the temperature rating is so that we can try to determine what that effect's going to be. Definitely find out temperature. A lot of times customers will apply these capacitive sensors in applications where if they're looking at water, for instance, as they heat it, they notice that their sensing distance isn't the same as it was when the water was room temperature. So we need to know what kind of temperatures they're doing if they're heating the water, because they'll notice that that sensing distance change as the temperature increases. So it is affected by it. Some other measuring products that we have are standard encoders, not the magnetically encoded, but optical encoders. These again are incremental or absolute. Absolute? How about absolute? Incremental and absolute. You can determine angles, distance, speed with these guys. We have IP69K versions, different interfaces. And you can, in the absolute versions, you can get single or multi-turn encoders. Another measurement solution we have are inclination sensors. There's basically 2 different styles. There's a single axis. You can do Modbus or an analog output 4 to 20. These use MEMS or fluid measuring technologies. There's 24 different versions of these guys, and then there's also the 2-axis, which is either voltage or current. Also uses the MEMS technology, and there's 16 different versions for these. So again, these you're looking at actual angles, but you can still measure that angle. Another big one for Balluff, one that kind of sets us apart from the competition, are the BLAWs, the light arrays. So as I mentioned before, we released the new family of these guys. They go from 16 millimeter active areas up to 100 millimeter active areas. You can put these up to 2 meters apart, but remember, when you put these 2 meters apart, your resolution is affected, and all of that's laid out in a manual how that's affected. 300 microns is the smallest part, and then we have resolutions down to 10 microns. Depending on the style that you pick, some of them have 2 analogs and 6 discrete outputs built into it. Some of them are IO link. Some of them have displays on the top to set them up. The only one that does not have the display on it is the 16 millimeter version. There just wasn't enough room to put the display in there. Another one is the new light bands or light grids, the old light grids. I would kind of go with the new light bands versus the old light grids that we had, the old BLGs, just because they don't really have the resolutions that the new light bands do. So there's 8 different versions of the new light bands. You can get them from 10 to 300 millimeters of active window. And then the distance between them can be anywhere from 10 to 50 or 10 to 500 millimeters. Your resolution depends upon this length. So the 10 millimeter version is going to have like 10 microns resolution. The 300 millimeter version is going to have 300 microns resolution. So it's a percentage of the active area. These guys can be used in level applications. So if you have a transparent container, you could look through that container. Also, if you have a sight glass, you could put these guys and look through the sight glass to determine what that level is with a continuous type output. If you're going to do this, again, you got to use the correct amplifiers. So you're either going to use the 0 to 10 volt or the 4 to 20 milliamp amplifiers. The next one is the pressure sensors. So these just went through the 2nd generation. We have 190 versions, which is actually a lot better than what it was before. We had probably close to 700 or 800 versions. You can get the false front. You can get them without a display. You can also get them in a tri-clamp, and you can get a standard version. You see all the different process connections, the different temperatures of that the media can be. And then also these are now IP69K. And then again, these can be used in level applications. More on these products in the near future. So what's that to say? We don't have any particular single technology that's suitable for every application. So the application determines the technology. So kind of what you see here, this is not the scale by any means, but these are some of the measuring or distance measuring solutions that we have. I've probably missed some, but these are the primary ones, I think. So again, we start really short range and then go all the way up to the longest range that we have, and also cost. These micrometers, the BLAs, are typically going to be pretty expensive, but basically they're a micrometer, so that's going to add to the cost. So that is kind of just a quick overview of what I just went through. One other thing that I found that might be of interest, and if somebody wants this, I'll send this out to them. I told Tim this morning, one of the new steps, that I was going to sell it to him, but I'll give it to everybody else because he's working on a project right now where he needs this information. But here's some common level sensing methods. Level sensing for us is a big thing. So basically some questions to ask when you see these applications. Excuse me. So some different questions to ask. What type of technology we have that would work for that, whether it's continuous or point level. On the capacitive section where you see continuous, out here it's highlighted in yellow. That's kind of a caution. That's using the standard capacitive technology. It is not smart level, so that one kind of you have to watch out for. And then the different medias, what this looks like. So like I say, I may just go ahead and put this up here for everybody if you want to keep this in your notes. So I know it was kind of quick, but that's basically what I have. Mr. Takis asked if there are plans for an IO link inclination sensor. Not that I'm aware of. Chris just said not with the current products, but they may be expanding the portfolio. So anyway, that is basically what I have for this. If you have any questions or whatever, I will send out that one slide. If there's other slides that you want, let me know and I'll send those out as well.